If you stop and think about the foundational technology that runs our modern world, everything from your phone to the power grid, how old do you assume the practical applied science behind it really is?
It feels ancient sometimes, doesn't it? Like something developed slowly over millennia.
Exactly.
Yeah.
But the sheer breakneck speed of innovation in electricity is just staggering. Much of what you rely on was actually developed in the span of a single lifetime.
And that kind of dizzying speed is the perspective we're taking today. We're diving into the work of Elisha Gray.
Right, the inventor.
Yeah, a major player in the field. He gave us this detailed snapshot of electrical science in his popular text, Electricity and Magnetism. Gray spent, 35 years actively working on electrical applications, including the early telephone.
And what immediately jumps out is Gray's own perspective on this speed of change. He notes that the older he gets, the less he feels he truly understands about electricity compared to, the immense amount that is still yet to be discovered.
That's the ultimate humility of a scientist, isn't it? Standing right at the edge of a new era. Absolutely. And he provides a crucial historical anchor for us. Gray observed that the applied science of electricity, the part that actually serves useful purposes, had mostly developed within the last 50 years, dating from his time of writing around 1900.
Wow, just 50 years for most of it back then.
Right. So our mission today is to understand that radical shift, the long, slow 2,300-year buildup, and then that explosive half-century that basically created modernity.
Okay, let's unpack this timeline then, starting with the ridiculously long wait. Our history begins around 600 BC with Thales of Miletus.
Thales is where it all started. He described the properties of elektron. That's the Greek word for amber.
Hence electricity.
Exactly. He noticed that if you rubbed amber, it would gain this peculiar power to attract and repel light substances, little things like feathers or straws. That simple observation gave the entire science its name.
And for 23 centuries, that was pretty much it, right? We had little ancient oddities maybe, but no real engineering application. They knew about animal electricity, for example.
They did, yeah. The torpedo fish was famous in antiquity. It could paralyze animals and men. We even have records that the fish was intentionally used by the ancients to cure ailments.
Seriously, like what?
Well, like gout, apparently, for a freedman of the Emperor Tiberius. But this wasn't really physics. It was more like folklore built on observation. For over 2,000 years, progress was basically limited to, parlor tricks involving rubbing things to generate sparks.
It took until Benjamin Franklin in the 1700s to finally give this static electricity some real gravitas. He showed that the static charge created by friction and the power of lightning striking the earth were actually one and the same phenomenon.
Franklin's ability to link those two was monumental. He demonstrated they shared 4 crucial characteristics. They move in crooked lines, they strike the highest points, they can fuse metals, and they destroy animal life.
And central to his ability to study and manipulate this power was the Leyden jar, wasn't it?
Yes. So after Franklin confirms lightning and friction are the same, the first real piece of electrical hardware that allowed people to manipulate and store this charge, that'd be the Leyden jar, invented independently around 1745 by a few people.
Okay, what was it exactly?
It was essentially the world's first capacitor, a device designed to store electric charge, usually a glass jar coated inside and out with tinfoil. The foil acted as the plates, and the glass was the insulating layer.
And storing that charge let Franklin develop his big theory.
Exactly. His famous theoretical contribution, the single fluid theory, instead of the popular idea back then that positive and negative were 2 separate fluids.
Franklin simplified it.
Right. He argued electricity was just one fluid. Positive was simply an excessive amount, while negative was a shortage compared to the normal natural amount. That simplification really made the concept of static charge finally manageable for scientists.
Okay, so if static electricity was the long, slow era, the next big jump, the discovery of dynamic electricity, the current started, kind of bizarrely, with dead frogs in 1790.
Ah, the Galvani incident. Yes. Luigi Galvani observed a dead frog's leg twitch wildly when it touched a scalpel near an electric machine. Galvani, he attributed this to animal electricity. He thought he'd found the source of life force itself.
But the genius of Alessandro Volta was to look at that same kicking frog and immediately realize Galvani had kind of missed the mark entirely.
That's the start of the Voltaic revolution. Volta correctly argued the action wasn't animal electricity at all, but a chemical reaction happening between 2 dissimilar metals, the scalpel and maybe another piece of metal, using the moist frog tissue as a conduit.
And this led him to invent
the voltaic pile. Basically, alternate layers of zinc, copper, and cloth, saturated with saline solution.
Volta literally invented the battery.
He did, founding the science of voltaic electricity. And of course, the unit of electrical pressure, or the push needed to move that current, is now named the volt in his honor.
That push being what we call electromotive force.
Precisely.
So from the battery, which gave us current, we leap to Michael Faraday, who provided the mechanical blueprint for generating power on a massive scale. His key finding contained the germ of the modern dynamo.
It's such a fundamental law of physics, but distilled into a really simple concept. Faraday found that if you jerk a piece of soft iron wrapped in wire away from a permanent magnet, you generate a spark.
Motion plus magnetism equals current.
That fundamental relationship, motion interacting with magnetism generates current, is the mechanical basis for pretty much every power plant operating today.
Okay, but here's where it gets really interesting, because Gray's text highlights this kind of bizarre paradox. Despite all this stunning practical progress, the Leyden jar, the battery, the dynamo's blueprint, the underlying theoretical understanding was still, well, a bit of a mess.
Totally. Gray quotes Lord Kelvin saying, "No real advance in explaining the actual nature of electricity had been made in 50 years.
So the application was running way ahead of the theory.
Exactly. Practical application was just racing ahead. Scientists were building things that worked, but they were working based on what Gray called elegant guesses. The prevailing speculation at the time was the ether hypothesis.
Ah, the ether. That electricity traveled through this, tenuous, highly elastic substance called ether that supposedly filled all space.
Right. So they were treating electricity as some sort of invisible fluid or wave moving through this invisible sea.
But Gray notes that wasn't the only idea gaining ground.
Correct. Gray mentions the growing acceptance of a much more modern theory, that electricity is actually a mode of motion of atoms, not a fluid at all. And the evidence he offers for this shift is fascinatingly simple, tactile even.
It links thermal and electrical conduction, right?
Yes. Gray noted that metals that conduct heat best, like silver, also conduct electricity best. And conversely, if you heat a conductor, you actually diminish its electrical power.
That correlation suggests that for electrical motion, the movement of the subatomic particles to have, free play, the chaos of heat motion has to be suppressed.
It confirms that everything is linked back to the physical movement of matter and energy, which leads us perfectly into magnetism.
Which is fundamentally tied to this atomic motion. The theory being that iron and steel molecules are themselves tiny natural magnets.
Yes, and when a piece of iron is unmagnetized, these molecular magnets are sort of paired off. They satisfy their own force internally, so no external magnetic force is felt.
And Gray gives a simple analogy for this, right, to help you picture it.
He does. Imagine 10 boys representing the molecules. Unmagnetized, they pair off into 5 pairs, each clasped together, pulling inward. Maybe they exert 100 pounds of force, but none of it is felt outside the group.
But once you introduce an external force, you magnetize them.
Exactly. They all line up, they all grab a rope, and they all pull in the same direction. That combined force is now external and visible. That's the alignment of molecules inside the iron that makes it a magnet.
And this analogy helps us understand why there are 2 types of magnets: permanent versus electromagnets.
Precisely. Permanent magnets are made of hardened steel. They retain their alignment because the close-grained structure holds the molecules in that polarized position by what's called coercive force.
Coercive force, like molecular stiffness.
Kind of. It's the force holding those molecules exactly where they were pushed, like a bent bow under strain, preventing them from snapping back easily. Soft iron, which is used for an electromagnet, lacks that stiffness.
So the alignment disappears the second the current is removed.
Right, and just for context, the Earth itself is one giant electromagnet, with its poles revolving once in about 320 years.
Okay, so now we move from theory and simple magnets to the wire era, starting with the galvanic telegraph around 1820. Oersted had discovered current affects a magnetic needle, but the practical long-distance problem hadn't been solved yet.
That solution is often credited to SFB Morse, but the underlying genius was really Professor Joseph Henry. Henry, back in 1835, worked out the relay system using a local circuit to boost the signal.
That was the key mechanism for long-distance transmission.
Absolutely. But Henry, being a pure scientist, never patented it.
Which opened the door for Morse.
Who was an artist. Interestingly, not a scientist, but he was excellent at marketing and execution. Morse developed the register and the now iconic dot-dash code, and he secured the first government line between Washington and Baltimore in 1844.
A classic case. The scientist provides the foundation, the inventor monetizes the application.
You see it time and again. And the application was robust. The versatility of the Morse code, once implemented, is just incredible, while most American operators favored reading by the sound of the clicking register.
There are some legendary stories of operators adapting the code using other senses, aren't there?
Oh, absolutely. We have the record of the deaf operator in Louisville who could read the message just by holding his knee against the table leg and feeling the long and short vibrations of the sounder. The code became a physical experience.
That's amazing.
And then you have General Stager, who, after a train wreck, apparently climbed a pole, cut the wire, and sent an emergency message. When receiving the reply, he held the two cut ends of the wire on either side of his tongue and tasted the current. A sharp metallic taste signaled the returning pulses.
He tasted the Morse code.
Wow, incredible human adaptation.
Yeah.
And my favorite is the blind sister, who, during a presidential election, was helping her brother read the returns using the Bain chemical system.
How did that work?
It emitted an odor when the current passed. When the lamp went out, she leaned over the stylus and apparently smelled out the election results for her brother.
Smell, taste, touch, incredible. But these feats were possible, yet long-distance telegraphy still had one major electrical hiccup: the kick.
Right. If you tried to send two messages simultaneously, what they call duplexing, the current coming back from the far end of the long line created this momentary surge, a kick, that interfered with the short artificial circuit used in the local instrument setup.
The line was electrically unbalanced.
Exactly. The long physical line took just a fraction of a second longer to fill with current than the short local circuit. This is where Joseph B. Stern stepped in around 1872 to perfect the duplex system by introducing the condenser.
The condenser measured in microfarads, named after Faraday.
Yes, essentially a large metal surface. It gave that short artificial circuit the same ability to absorb or store charge, the same electrical capacity, as the long real line. This equalization cured the kick and truly perfected long-distance simultaneous signaling.
Speaking of fundamental fixes, let's bring it back to Elisha Gray's personal journey, specifically to the telephone. He was working on musical harmonies telegraphically, but the key insight came from a surprising observation in Milwaukee.
Ah, the lover's telegraph. Yes, two fruit cans connected by string where two boys were apparently conversing across the street. Gray saw that simple mechanical vibration transferred through tension, and it sort of clicked. It solved the problem of articulated electrical speech in his mind.
And that led him to file the first complete description and caveat for a speaking telephone.
It did. And the mechanism is beautiful in its simplicity. It relies on the magnetoelectric principle. You have a permanent magnet, a spool of wire, and a thin iron or steel diaphragm. Sound waves cause the diaphragm to vibrate.
And that vibration actually molds the magnetic field.
Yes, which induces currents in the wire that correspond exactly in number and complexity to the sound waves of the voice. When those complex patterns of current reach the receiving end, they cause the receiving diaphragm to move in exact sympathy, reproducing the spoken word.
The complexity of human speech replicated through metal and wire. Amazing.
It really is. And that brings us to the final monumental stage of electrical history that Gray chronicled: the mass generation of heavy current, specifically thinking about Niagara Falls.
This marks the transition from communication telegraphs, telephones, to raw industrial power, harnessing the massive, constantly wasting energy of Niagara. What was the drop there?
A 165-foot perpendicular drop, plus another 100 feet of gradual drop to exploit. Huge potential.
And the dynamos installed there were massive AC generators, right? 5,000 horsepower each.
Enormous for the time. And to simplify the engineering, they opted for a design using revolving field magnets and a stationary armature.
That's a critical choice. Why?
Well, by keeping the high-power coil, the armature stationary, they avoided the huge headache of trying to run high-voltage, high-amperage current through moving parts, through brushes and commutators.
Much simpler and more reliable for that kind of power.
Absolutely.
Yeah.
It's an example of brilliant, practical engineering triumphing over complexity, and critical to keeping those 5,000 horsepower machines stable was the governor.
The governor?
Yes, it constantly adjusted the water flow to the turbines to manage the constantly changing electrical load being drawn by Buffalo and the surrounding areas.
Yeah.
That governor was continuously standing guard, ensuring stable power generation.
Makes sense. But the key to distributing all this power economically over distance was the transformer, wasn't it?
Absolutely essential. The dynamos initially output a usable 2,200 volts, but for long-distance transmission, say 20 or 30 miles to Buffalo, they had to step up that voltage way higher, to 10,000 volts, for instance.
Why bother stepping it up so high?
It comes down to a fundamental physics principle: resistance loss.
Right.
You lose power as heat in the wires, and that loss is proportional to the square of the current. Remember, I squared R loss.
Right.
So by massively increasing the pressure, the voltage, you drastically decrease the current needed to deliver the same amount of power.
Which saves a fortune on copper wire.
Exactly. You can push the power through smaller, cheaper copper conductors with far less power lost along the way. It was the invention of the transformer that really made centralized power generation economically feasible.
And this cheap, heavy, mechanically generated current, both alternating current, AC, for heat and power, and direct current, DC, for chemical processes, led to a rush of new, massive industrial products. That defined Gray's new era.
Yes, three really stand out, showing the versatility of the current. First, carborundum, a new diamond-hard abrasive.
How is that made?
It required intense heat generated by electrical resistance in a special coke core furnace. That furnace alone used 1,000 HP.
Okay, what else?
Second, aluminum. Once a prohibitively expensive luxury metal, right? It was cheapened dramatically by an electrolytic process.
Which needs DC current.
Yes, low voltage, direct current to chemically decompose the source material. That process alone consumed something like 30-50 HP per conductor line. Massive energy use.
And the third?
Calcium carbide. Used to produce the bright acetylene illuminating gas, manufactured using the intense heat of an electric arc light to unite lime and carbon. So you see electricity driving chemical production, materials, science, everything.
Gray really emphasizes that this truly is a new era. Just 57 years after that first telegraph line ran in 1844, electricity was controlling time, reporting the commercial pulse of the world, powering transport, providing light across vast distances.
It's astonishing, really, that so much of what defines modernity, from telecommunications to industrial chemistry, happened in such a short, compressed century, especially following 23 centuries of almost zero practical progress.
And this rapid succession of marvels became the new normal, didn't it? So much so that Gray closes with this really profound observation.
He does. He says the human mind became so accustomed to these periodic revelations of the marvelous that it now needs the stimulus. We don't know where the development will end.
But no one, absolutely no one, believes it has ended. It leaves you with the challenge, doesn't it? Given the theoretical leaps and the industrial applications we just discussed, what massive, unpredictable, new electrical or theoretical breakthrough is right now waiting in the wings, just beyond our current understanding?